Introducing Altivity, Canon Medical's bold new approach to AI innovation. Using only the latest AI technologies, Altivity lays the foundation for a smart and ambitious future, powered by advanced AI capabilities. High-quality images for enhanced diagnostic confidence and informed treatment decisions. Reduced exposure dose with fast, accurate results for a more tailored treatment approach. Simple, streamlined workflows that optimize resource deployment and increase efficiency. Because when you turn your data into a truly essential asset for you and your patients, the possibilities are endless. Altivity. Intelligent healthcare made easy.
Hello, everyone. Good morning, good afternoon, good evening. Welcome to Canon Medical's Artificial Intelligence webinar, where we'll be exploring the future of intelligent healthcare, AI today and beyond. My name is Rich Mather, President of Canon Medical Research USA, and I will be your host and moderator as we hear from two of the world's experts in medical AI. I expect some thought-provoking questions will be raised. You might have noticed that AI is everywhere these days. We believe it shows tremendous promise to revolutionize nearly all of the work we do. At Canon Medical, we're leveraging AI to create richer, more precise images, to aggregate and analyze both biologic and imaging data to open up critical clinical insights, and to streamline workflows into efficient solutions that can help make precision medicine a reality in a value-based care world. As a company with a long history of delivering innovations in imaging, we'll start with the image. Our advanced intelligent ClearIQ engine, which is our deep learning technology, reconstruction technology, across all of our modalities, we create higher resolution images with lower noise to lay the foundations of these clinical insights. However, we know that imaging alone can't deliver all of the necessary information, which is why we're expanding our in vitro diagnostic methods to bring earlier and more accurate clinical information through biologic tests and assays. And finally, we're binding these rich data sources together by aggregating and analyzing it all to deliver intelligent clinical insights into the hands of every member of the patient's care team. Through our automation platform and clinical cockpits, we deploy solutions like AutoStroke that aggregates all relevant information, automatically analyzes the data for hemorrhage and large vessel occlusion, calculates the perfusion maps, and delivers these key insights to the care team so the best and most informed decisions can be made for patients when time is critical. Altivity represents our unique approach to AI innovation. It aims to deliver informed healthcare through high-resolution images with exquisite precision, to enable fast, tailored care by consolidating every bit of relevant data to ensure the key clinical insights are made, and to unlock efficient workflow to ensure these insights are accessible, accurate, and presented intuitively. Our first speaker today is Professor Elliot Siegel, who is the Vice Chair in the Department of Radiology and Nuclear Medicine at the University of Maryland School of Medicine. Professor Siegel has been a longtime champion of digital imaging and is a world's expert on the promise and application of artificial intelligence in radiology. Today, he will talk to us about breaking new ground with AI. Please help me welcome Professor Elliot Siegel.
Thanks, Rich. I really appreciate that introduction and the opportunity to be able to share some insights on breaking new ground with AI. I'm looking forward to Bram's discussion and some of the questions as well, and I think this should be a really interesting and hopefully interactive session. One of the things that AI today reminds me of is back in 1993, when I had the opportunity to help set up the world's first filmless radiology department, and we made the transition from film to digital, and we were super excited about having any image available anywhere, anytime. And secondly, the potential to be able to have these images available for computer digital enhancement and diagnosis and detection. Back then, we were told we may be opening Pandora's box and letting all the images out from radiology to surgeons and ER docs. And, there were lots of excitement, but also lots of fear about the implications of that. And here, kind of ironically, again, we're sort of groundbreaking AI. And in many ways, this also has generated a tremendous amount of excitement and some level of fear about opening Pandora's box with regard to decreased need for radiologists or even potentially replacing radiologists. There's incredibly exciting promise associated with improved accuracy, efficiency, safety, and better exchange and more consistent exchange of information associated with AI. And I'd like to talk a little bit about some of that promise. So when we talk about AI, what is and what isn't AI? Well, the term was originally coined by a computer scientist at Stanford, John McCarthy, all the way back in 1956. But most of what we talk about when we hear about AI today is actually deep learning or the use of a convolutional neural network. It's essentially the modern version of computer vision. Ezekiel Emanuel, famously, at the American College of Radiology meeting in 2016, gave a keynote suggesting radiologists may be replaced by computers in the next 4 to 5 years. Here we are, 5 years later, and certainly there has not been any significant move in that direction. And so I guess I'd just like to start with just a couple minutes about whether radiologists will be replaced by AI. And of course, I have absolutely no fear that that's the case. And in fact, I'm incredibly excited at the prospect of being able to work closely with AI and in conjunction. The big mistake that Hinton and Andrew Ng and Ezekiel Emanuel and others have made is that we've made incredible advances in being able to detect what's in an image using the Stanford ImageNet set and others. And so computers are faster and better than humans at determining that there is a TV and a spoon and a fork and a snowman in this picture. But what's wrong with this picture? The computer, unlike a 5-year-old, doesn't know a TV doesn't belong on the roof, or a spoon and fork shouldn't be that large, or a snowman shouldn't be there without snow. And so any 5-year-old could probably beat the strongest supercomputer in the world easily in the task of what's wrong with this picture. And the fundamental challenge, I believe, that is beyond computers at this point, despite the fact that they have so many amazing things that they can do, is really understanding what's wrong with this image. And this judgment that radiologists have is a really difficult thing. And so that's why I believe that it's a difficult thing for computers. That's why I believe that computers will not replace radiologists, but will work hand in hand with radiologists. And in fact, in 2011 in Scientific American, there was an article suggesting that this image test of what's wrong with this image may be the ultimate test of computer intelligence rather than the Turing test. And we talk about MRI and CT and ultrasound and PET, et cetera, but even reviewing and interpreting an ICU chest radiograph is really hard to do, and it's really a major challenge. And so it turns out that we can use neural networks and assign a variable to each one of the pixels in an image. And for medical images, because the images are so large, in general, we downsample to matrix sizes that are smaller, less than 400 by 400 typically. And so one of the questions is, how have we changed our paradigm with what we call the modern era of AI? And if you take a look at this Where's Waldo image, you may recognize the challenge of trying to find a match in all of these people in these images with Waldo. And some people are really excellent. They can find Waldo right away. Some people take a little bit longer. And so if we had to program an algorithm to find Waldo using conventional techniques, we would end up doing feature extraction and looking for Waldo's unique shaped face and his round eyeglasses and his hat and his smile. And it might take months or years to be able to do that feature extraction and then be able to do segmentation and then be able to subsequently be able to apply machine learning and create a probability. But what if we could just learn, or what if we could teach our computers the way a young child learns, and that is by example? And so what convolutional neural networks allow us to do is to be able to learn, have computers learn by example. So if we had millions of images, either with or without Waldo, that would be one way to train a system if we told them which ones had Waldo. Even better, it would be ideal to circle Waldo and find Waldo, and then we wouldn't need to have as many samples or to train. But what really is the difference is the ability for the algorithm to essentially be extracted by example from the images. And so if you think you found Waldo here, this is actually a false positive Waldo. The real Waldo has a square chin and round glasses and essentially no teeth like this. And so here is where the real Waldo was if you were looking for him. What are the implications of deep learning in radiology? Well, it may take 3 to 5 years with multiple complex steps of segmentation, feature extraction, support vector machine to create a CAD algorithm as was done for mammography many years ago. Now we can create algorithms to do the same task from examples from annotated data sets in just hours or even days. The problem and challenge is it takes similar amounts of time to test and to validate these algorithms as it always has. And so it's much, much longer to validate these and to essentially get regulatory approval, even though FDA is doing some pretty innovative things with pre-check to validate a particular company and its algorithms and other approaches. In fact, what I find most exciting about what the FDA has been talking about recently has been the potential to take advantage of the fact that AI algorithms might be able to dynamically learn and change once they're released to users. And so this is from a talk that was given by the FDA looking at adaptive automated algorithms that might actually learn and change as time goes on. We don't have this in the marketplace yet, but it's really exciting that they're looking at the ability to potentially retrain with additional data sets for algorithms, or to be able to expand the input data type and add additional inputs into an existing released algorithm, or even to expand the population on which an algorithm is being applied. And so these dynamic changes, I think, will completely change the way we think about consuming these algorithms so that they can learn in a manner similar to the way my residents and fellows learn. As far as rethinking PACS, I think the pandemic has made us accelerate our thinking about different possibilities for PACS. And I think the days of PACS itself may be numbered as best of breed applications replace PACS. I don't want to necessarily have to download or buy the entire CD to just hear one song. And I think the idea of being able to stream my favorite songs is analogous to what I'd like to do by being able to essentially stream my favorite AI applications in radiology. This is from an article that we published in the JACR suggesting what might it be like if we could consume AI algorithms and also other PACS functions such as storage or visualization using a platform similar to the Apple platform or the Android platform. So what are some current non-pixel-based groundbreaking advances? Because we've mainly talked about pixel-based ones where we're looking at images. Well, one that I think is really interesting has been AI applied for reduction in patient no-show rates. And it's been suggested by Chang et al. In their article that they could achieve a 17% reduction in no-show rates that was persistent after they ended up applying AI to look at reducing patient no-shows. Here's an example of an algorithm that looks at the body of a radiology report and generates the impression based on many previous reports that a radiologist has created, with the potential to speed things up by 24% of the total time that radiologists spend. What if AI were only able to read cases where it was pretty confident in its detection and diagnosis? And so this is an article that was published suggesting, well, maybe we don't have AI interpret all of the studies, but what if AI were able to achieve a 0.99 negative predictive value? If there was a 15% prevalence of disease, it could exclude 34% of mammograms. And in a more realistic 1% prevalence of cancer, potentially an AI algorithm could operate at that 0.99% negative predictive value and interpret 91% of mammograms, where the radiologist potentially would only need to interpret 9%. So, thinking dynamically and out of the box about the potential for how we might work best between humans and AI is really interesting. How about reimbursement for AI? We all are wondering about the economic model. And increasingly, at least in the US, we're seeing CMS and other insurance companies consider reimbursement. In a groundbreaking development, there was a technical fee for reimbursement for reimbursing an algorithm that looks at large vessel occlusion in patients with suspected stroke. Other possibilities that I think would be really interesting for that CMS reimbursement would include a triple rule out for chest pain in the ER, assessment of intraperitoneal blood in trauma patients, evaluation of C-spine fractures, and evaluation of the chest in COVID patients to predict who should be hospitalized. And even also promising has been the emergence of at least a test CPT code for automated analysis of possible vertebral fractures incidentally seen on CT, or determination of bone strength and the potential for fractures using finite element analysis. What is going to be the initial killer app for AI? What is today's killer app from my own perspective? And the answer to that is actually AI embedded in reconstruction algorithms for CT, MRI, and PET scanning. And I think that we're going to see more and more application, and it will be ubiquitous for application of AI. Some of this work is based on a variety of different techniques, including generative adversarial networks. This is an algorithm that generates synthetic faces using AI. And this is just an example of how a generative adversarial network might work, where you have one algorithm that detects counterfeit bills, another algorithm that essentially generates new counterfeit bills, and then the algorithm that detects them ends up getting better and better, and the algorithm that is the fake to create the counterfeit bills gets better and better, and they end up teaching each other. And that's similar to a approach that is used to improve images and reduce noise. And so I think that for MRI or PET or CT, we're going to see and are already seeing major changes with major important implications. Here's an article from Stanford that suggested dose reductions that were really dramatic in, and also time reductions that were really dramatic for PET imaging. And for CT, I think we're just scratching the surface looking at noise reduction. And I think we can reduce artifacts, reduce motion artifacts, and essentially be able to derive model-based iterative reconstruction from statistical-based iterative reconstruction, so that we can save and turn what used to take hours to do into fractions of a second. And so I think that the potential to be able to have a database of model-based and also statistical-based iterative reconstruction in order to reduce noise has been a really super promising approach. We're using that approach as we look at ultra low dose CT scans, potentially in the neighborhood of 0.2 millisieverts or so, and applying these technologies to significantly improve image quality and reduce noise. Another application of AI is toward precision medicine. I think we can make screening significantly smarter by determining which are the patients that actually are at highest risk for developing disease, not something just as a simple algorithm like smokers over a particular age. And so one of the projects that I've worked on is downloading a database called the PLCO database of about 155,000 patients, and looking and following those patients for about 15 to 20 years, and then determining things such as certain ethnicities like Native Hawaiian or Pacific Islanders may have a 6-fold greater chance of developing lung cancer than a Hispanic patient, for example. And being able to take that information and put it into an algorithm where we have multiple variables that can create an a priori probability of disease, so that an AI algorithm can take into account a patient's cancer history or family history or smoking history or age or location of nodules, et cetera, and determine then, for patients, which patients should be screened. It may be that Pacific Islanders should be screened at an earlier age or with or without a smoking history. With regard to automated image interpretation, there have been so many really interesting applications and so much of the AI literature that's been devoted to that. But as I mentioned, looking at using AI for quantitative assessment and also to improve efficiency and productivity, I think are really interesting. There have been some really large data sets that have been available with regard to lung nodules, bone age, and most recently COVID that have driven a lot of the AI development, and that's been great. But I think we need to develop AI algorithms based on clinical need. And so some of these algorithms that are around, such as breast cancer detection, pulmonary embolism, intracranial bleed, large vessel occlusion, emphysema, identification of life support lines, are available now pretty widely and do, I think, have really strong clinical impact. If I had to create a wish list of the ones that are not available that I'd like to see, they'd include thyroid nodule detection and tracking on ultrasound, lymph node detection, detection of head and neck cancer on CT, lung cancer follow-up, congestive heart failure, retained sponges or clamps or towels in the OR, ICU chest interpretation, MR of the knee and hip interpretation, quantification for osteoarthritis, rib fracture detection, and CT or MR liver lesion characterization. Another amazing application of AI is in image segmentation and the ability, for example, for an AI algorithm to find the adrenal glands and then to determine on CT their fat content or look at contrast enhancement once they've been segmented, or determine whether or not there's enlargement of the liver, spleen in a quantitative way, I think is really exciting. And one of the things I think will be coming soon will be much more ubiquitous application of population health applications, looking at bone mineral density, coronary artery calcification, abdominal aortic aneurysm detection, gallstones, and renal calculi. And then I think what's also exciting with regard to AI is quality control, optimizing quality for conventional mammography, optimizing quality of IV contrast injection, and also looking at optimizing the trade-offs between CT dose and noise quality, and even positioning for chest radiography. What do I think is going to be a killer app maybe 5 to 10 years from now? Well, I think it's really going to focus on efficiency and productivity. And so here you can see Lucy and Ethel on the candy factory that I think is a great metaphor for the idea that we are increasingly feeling as though we're on an assembly line. And I think a killer app that could actually improve efficiency would be amazing. We've done research at our facility when we first made the transition to PACS and found that we're only about 15% efficient with regard to application of PACS. And this radiology practice uses 6 scribes, and they're able to increase their productivity by a factor of about 6 to 7-fold, which is incredible. Would it be possible for AI to do what these 6 scribes do and maybe increase productivity for radiologists by 50% or more? I really believe that AI offers the potential to do that. And then, if you ask patients, what is it that they want from their doctors? It's not necessarily to be at the top of their class in medical school or to necessarily have achieved certain, certificates or board exams, but they want their docs to be confident, humane, personal, respectful, forthright, and empathetic. So in conclusion, the transition from film to digital imaging for the last 30 years or so has brought about ubiquitous access to images, but also the tantalizing promise that we had hoped for almost 30 years ago, that AI could be used to allow us to practice medicine and to achieve earlier and more accurate detection, diagnosis, and treatment. But I think 30 years later, we're just beginning to realize the groundbreaking potential of AI. I think it's going to undoubtedly have a major impact that's positive on accuracy, discoverability, safety, and efficacy in diagnostic imaging, and it's going to revolutionize the practice of diagnostic radiology. It will allow radiology and radiologists to stay relevant and I think allow us to enter the dawn of the era of personalized precision medicine finally. And I'm looking forward to the day, hopefully soon, when AI will be so seamlessly adopted and incorporated into routine practice that it will become, as Professor Van Ginneken is about to tell us, practically invisible. Thank you very much.
Elliot, thank you so much. That was excellent, as always. Thoughtful,
Thanks.
provocative. I really like the way that that you see our future working with AI. Thanks so much. We're going to move over to Professor Van Ginneken's talk, and then afterwards we'll have some time for Q&A overall. So next, I'm pleased to introduce Professor Bram Van Ginneken, who is a professor of medical image analysis at Radboud University Medical Center. Professor Van Ginneken is also a prolific author and innovator developing medical imaging analysis software. Today, he's going to take us through the journey of AI in radiology from promise to invisibility, as Elliot just mentioned. I'm sure it's going to be a fascinating one. Please help me welcome Professor Bram Van Ginneken.
AI in radiology from promise to invisibility. These are my disclosures and disclaimers. And before we start with going to invisibility, let's say that let's talk about the way we went from promise to reality. So I want to give one example. This is my PhD work that I started to work on in 1998. And the task here was to detect tuberculosis on a chest X-ray and to write a computer program for that. And I used a classical machine learning approach. So I segmented the regions in the chest X-ray, computed texture features, and used support vector machines like Elliot Siegel mentioned in the previous talk to make a classification of the image. So this was all nice in the days, and I wrote a publication about it. I wrote a thesis about it. But actually, the software I had developed was not on par with a radiologist assessing the image. So it wasn't good enough in the days at the time. However, we kept working on it, and later got funding to also install a couple of digital chest X-ray machines in various countries in Africa. You see some pictures here from Zambia, and we had new PhD students working on it. And the interesting thing was when we then made a better version of the algorithm and installed it in Zambia, doctors there immediately started to use it because they had a complete lack of readers of the X-ray images. Yeah, and that was even before it was certified. So that was very scary for me, but it also showed to me that if you develop something for which there is a very big need, people will start to use it. Now in 2014, we eventually CE certified the algorithm. And then actually it was taken up remarkably quickly, and it was used in a few years later in over 30 countries, screening around 5,000 X-rays a day at the time. However, in 2016, the WHO, they had convened a group of experts to look at the evidence for using this computer-aided detection for tuberculosis. And they concluded that a review of the literature showed that they could not yet recommend to use this. The evidence was too limited. And they also concluded in this report that every chest X-ray should also be evaluated by a radiologist, because there could be other abnormalities besides TB on the X-ray, which is completely true, of course. On the other hand, it is used in countries where there's a lot of TB, and in those countries you don't have radiologists typically. So I expected that after this recommendation, the uptake of the software would actually go quite slowly. But to my surprise, more and more organizations started to use the software because they could take the responsibility, and the WHO is not a law-making body. So it was actually used more and more in big screening programs like the pictures you see here from Pakistan, where people would line up in front of a bus, get their X-ray taken, and then the computer, which our software is typically running on a small computer like this next to the X-ray machine, would immediately say which of these people had to go to the back of the van, cough up sputum, and then they would get a PCR test to confirm TB, and they could be put on treatment immediately. So despite the recommendation, the uptake of the software was quite rapid. And then very interestingly, and for me, this was also very satisfying after starting to work on this in the previous century. Actually, this year, the World Health Organization made an update of that recommendation in a new report, they now actually recommend to use computer-aided detection software programs in place of human readers for interpreting digital chest X-rays. And they did this because between 2016 and 2021, a lot of studies came out wherein this kind of software now available from various vendors was evaluated and shown to work better than human readers. This is one such study that came out recently using a very large data set from Bangladesh and evaluating the performance of 5 different commercially available software packages. And all of these packages performed better than the average of a radiologist in Bangladesh reading these X-rays for as part of their work. So this is a very big change and really has made this AI going from promise to reality. Now, this was an example for tuberculosis, but this happens, of course, in many other areas. In the previous presentation, you already saw some results from mammography screening. This is a nice study that came out recently from a group in Sweden, where they evaluated 3 commercially available software packages, and they showed that the best of the 3 packages actually outperformed the 2 readers, the average of the 2 readers that were used in the screening program. And then the same author group made an interesting study where they looked at the performance of this best software program and proposed the following diagnostic algorithm. Let's say that you have your cohort, AI inspects all the images, and the 60% of the mammograms with the lowest AI score, you don't let a radiologist look at these images anymore, you just let these women come back in the next screening round. The remaining 40% is then double read. So this is from a European setting where we use double reading in mammography screening. And obviously the abnormal ones are then further followed up. But if the human readers declare the mammogram normal, but AI gives it a very high score, they suggest to do supplemental imaging, for example, MRI. And they show in this retrospective study that this actually reduces the workload for radiologists by more than half, but it detects more cancers. And then they conclude the article by saying that such validation should be done in other settings, and also a prospective trial would be needed to validate our findings. And in the previous presentation, you already heard that the time it takes to bring something to the market is actually, in practice, quite an obstruction. And I think it would actually be a mistake to do prospective trials to validate algorithms like this, because these prospective trials would typically take like 5 or 6 years. And when you're 5 or 6 years later, the AI software that you used in this trial will have been outdated, because the 10 or so vendors of mammography software, they still bring out new versions of their software almost every year. So the performance of the software increases over time. So we need some kind of mechanism to keep track of validation and make sure that good algorithms can go to the market quicker than first going through prospective trials. Now we have these interesting products, but are we there yet? Are they widely used? And that's related to reimbursement. So let's look at that. This is an interesting study that also came out recently from a group in Switzerland, where they made an overview of all AI software that has approval in the United States by the FDA or in Europe. So across all areas of medicine. And what they showed is that the number of products coming on the market has rapidly increased year by year. So we really have a lot of products on the market now with approval for clinical use. And what's also interesting to see is that actually radiology comprises more than half of all these products that are on the market. So and now I think gradually you see these products going into other areas of medicine as well. This has to do with the fact that these convolutional neural networks are so successful at image analysis, which is of course key in radiology. Now we've made an overview of all the products that are commercially available in Europe. We have this on our website, Grand Challenge, where we also conduct competitions between groups to develop these kind of algorithms. And you can also upload your algorithm here. So research versions of algorithms for many of the tasks that Elliot Siegel mentioned in the previous task are available on this platform. But there's also an overview of all commercially available products. And it's interesting to see that as of today, we already have 185 products with CE approval on the market. You can do all kinds of searches here on this website to zoom in certain areas. Like these algorithms are available through the new Canon AI engine that was announced at the beginning of this lecture. And these 185 products are coming from 83 different companies. So it's really a wide variety of companies developing these products. And many of these companies, as you can see here, have been founded relatively recently. So all of this has come mostly on the market in the last 5 years. So Jeffrey Hinton's statement that it will take 5 years to make software that's better than a radiologist, and at least last 5 years, a lot of software has come on the market, and all this software is using deep learning. Interestingly, when we had on our website the first 100 products available, we wrote an overview article where we also looked at for how many of these products is there peer-reviewed literature available about its efficacy. And we found that actually for 64 of the 100 products, there was no peer-reviewed evidence available. So I think this is something that needs to improve. For some products, there are very nice studies that show that, and this is just one example I want to show, a recent publication from radiology, a reader study with software from a French company, BoneView. It's a nice study. It also shows that this fracture detection software has high performance. But what I found most interesting in this paper was the small section where they said something about how the software worked. And interestingly, it was very simple. The company had collected a lot of radiographs in which fractures were indicated, and then they put all these images into a standard neural network detector called Detectron-2. This is open source software from Facebook that everybody can download. It has not been developed specifically to analyze medical images, but they turned it on, and that was their product. So indeed, it is now much easier to quickly make such a product as when you have collected the data. We can use standard algorithms for solving all these different tasks. And I think we still need much better standard algorithms for 3D tasks, but they will become available in the next few years. So we have a lot of products now, many without evidence. And in Europe, my feeling is that more evidence is probably needed before you can convince authorities to supply reimbursement for these products. Also, most products focus on improvements in reading accuracy and actually few on the reduction of workload, as was mentioned previously, and as I showed in the examples with tuberculosis and mammography screening. And I think that is the way to go, because in the Netherlands recently we had a report by the highest council that advises the government, and there's a lot of discussion about it, because it was a very tough report, basically saying that the way we are handling healthcare is not sustainable. Healthcare is the only part of our economy that keeps growing. And they show in this report that when I was born in the 1970s, 7% of the population was working in healthcare. It's now 15%. And if you look at the projections and take into account the aging of the population, this will go to 33% in 2060. So stop training radiologists is about the most stupid thing you could possibly do. But we really have a problem. We cannot afford to have 1/3 of our population in healthcare. So we really need to do something about that and reduce workload, put AI. I think AI is part of the solution here, because it can streamline a lot of processes so that we can do all this healthcare that is coming at us with a reasonable workforce. Now, the last part, now going toward invisibility. I think this is actually starting to happen already, that as these AI software packages don't have reimbursement, and this AI software exists, AI software is actually integrated into more and more products and services. And the users do not always notice that there is AI in this particular product or service. So I want to give a few examples of that. This is a service that we are doing with a company that I helped found, Tirona. What Tirona does is they analyze CT scans from, I think, around 500 hospitals all over the world. And these are CT scans of COPD patients that might be eligible for one-way valve treatment. So what you do then is you put one-way valves in the airways going to the most diseased part of the lung, so a lobe that is hyperinflated, and the idea is that air can only go out via these valves, so this lobe will collapse, and the relatively healthy tissue in the lung has then more space again to breathe. The problem is not everybody is eligible for this treatment, because if you have incomplete fissures, then the air that's going out of the target lobe actually comes back via the holes in the fissure, and the lobe doesn't collapse. So what Tirona does is they make a report where they show the completeness of the fissures, and they show the emphysema scores for every lobe, and then the pulmonologist can decide whether or not to treat this patient. And this whole analysis is driven by AI, but the customer doesn't really see that. It's also checked by a human analyst, because the AI software is also continuously improved. So the customer just gets a report, but it's in fact a lot of AI happening behind the scenes. Here's another example of a project that we've been working on for a number of years. We want to bring ultrasound screening for pregnant women to countries where this now is not done. And those are actually the countries where maternal death occurs. We first made our own low-cost ultrasound device, and it was a very cheap device made by a 3D printer. Unfortunately, the image quality was not good enough, so we had to do away with our own device. But nowadays, you have all these cheap ultrasound probes that you can connect to a tablet or a smartphone on the market. And we are using this particular one. And what we did is we built an app where you'd simply make 6 sweeps over the belly of a pregnant woman. And these sweeps are guided by AI. If you don't make them correctly, if you don't apply enough gel, if you don't push hard enough, the phone will immediately beep and tell you to repeat the procedure, because it's constantly doing an AI analysis of all the images. And then the images are analyzed, and we have now transferred this to a company, the same company that we work with in the TB screening, and they will bring this on the market. And this can be trained to any midwife in 2 hours. And the app will tell you if there are twins, what the head circumference is, so when the expected date of delivery is, and whether it's a breech or cephalic position, because with a breech position, you have a high-risk pregnancy. And this is really aimed at getting women with a high-risk pregnancy to deliver in a clinic and not at home, and thus reduce maternal death. And it's all doing AI and deep learning, but the typical user doesn't see that because it's built into the product. And here's a final example, was already mentioned. We now have exquisite reconstruction algorithms that use deep learning and that actually produce much nicer images. And here's a recent publication from Japan looking at the ACE reconstruction from Canon. And what they show is that if you have a slim and an obese patient, then with normal reconstructions, the quality in the obese patient is lower. But if you use the deep learning based reconstruction, actually the quality of this image is nicer than the normal reconstruction of the slimmer patient. And here's another example of 2 patients where you have the standard reconstruction, and with the deep learning reconstruction, you get much nicer image quality. And this is now called ACE, so you can assume, oh, there must be AI in it. But what we will see is that these kind of algorithms based on deep learning will be integrated in more and more algorithms. So gradually AI will become invisible. So the future of AI is to use these products. There are now almost 200 certified solutions available. They are not yet widely used, so I think this will increase over the next decade, and that has to do with limited scientific evidence, but also the fact that it is expensive and time-consuming to do validations that may be needed in order to get reimbursement. And if the demands for these validations are too excessive, this may actually drive up cost and lead to only outdated AI being approved. So that's something I think we should try to avoid. Now, these AI solutions will be provided as a tool for the radiologist, but if you have to pay for them separately, it may increase costs, and it is still a challenge to integrate them perfectly in the workflow. I really hope that these kind of app stores that the previous speaker showed will become a reality. But if you look at what is available now, there are not that many solutions yet that focus on full automation of parts of the workflow. So the parts that maybe are also the most boring or repetitive for a radiologist to perform. And I think that is what we need to focus on. And AI becomes integrated behind the scenes, I think, in more and more products and services, and in fact may become invisible. And that sounds like a sad thing, but it's actually very typical of AI. So this is called in the literature the AI effect. Ever since we started with artificial intelligence, as soon as artificial intelligence could do something, then people were arguing, yeah, but that is not real intelligence. So one researcher, Rodney Brooks, complains that every time we figure out a piece, it stops being magical. We say, oh, it's just a computation. So basically the AI effect says that it's a redefinition of what AI means. AI is anything that has not been done yet. Now, I hope that AI will do a lot of things, and I don't really care if we then still call it AI. So from my point of view, it may become invisible, but I think it will be a super useful addition to radiology. Thank you for your attention.
Bram, thank you. That was fantastic. Really, again, provocative, interesting. You raised a lot of very interesting points. You've done some really good work in kind of bringing AI out to the world, which is tremendous. We've got a number of questions coming in, and we'll try to get to them. Please keep them coming, and we have about at least another 10 minutes, but we can go a little long if the conversation keeps going. And I will say, Bram, the thing you just mentioned at the end reminded me very much of sort of Arthur C. Clarke's famous statement that any sufficiently advanced technology is indistinguishable from magic. And right now, so much of AI seems like magic, but as we learn more about it and get more comfortable, we'll start to understand what it's actually doing. And I think that is actually maybe a great place to start. Is one of the most important things about AI is it does feel so much like a black box right now in so many cases. Are there, do you see efforts, either one of you really, Bram or Elliot, please answer. Do you see efforts that are promising that can help, they call it maybe explainable AI or things like this, but that can help the users or the recipients of the information from AI feel more comfortable about what they're getting and not just feel like, well, the computer says so, therefore it must be true. I think that, as scientists, we're all far more skeptical than that, and that's good. But what do you have to say around those things? Either one, please jump in.
So I could start by saying, if you look at what a radiologist needs to do to report on a specific exam, there are many, many guidelines and structured reporting systems that basically say step by step what you should report on. So you should not have an AI system that just says this CT scan has lung cancer and that's the only information you get, because then it's indeed completely black box. But if you look at for screening at the lung RADS guidelines, they specify quite precisely that you have to indicate the nodules, you have to say what type of nodule it is, you have to give the size, and from that you get to a certain lung RADS group, and that determines your follow-up. And we have made a product that really automates all these steps and gives the AI segmentation, so the radiologist can check if he agrees with the statement that this is an 8 millimeter nodule. And I think this is the way to go. And if you do full image classification, then with heat maps, like what I showed for the TB software, there are many standard ways where you can give feedback what the computer is doing. And you should do that. And I think most of the good commercially available products work like that. So I'm not too concerned about the black box argument, but I don't know what Elliot thinks about it.
Well, yeah, I mean, so I'm certainly concerned about the black box question. And it's really the question of explainable AI. And I think, as Bram says, there's lots of ways around it. But it reminds me of the dilemma that we've had with mammography. I mean, 89% of mammographers in the US indicated in a survey that they used mammography. Practically none of them indicated that they trusted it or that it changed their diagnosis. And part of the question is why? In other words, what happened? I mean, none of those mammographers actually save their CAD markings. And so I think that the problem was, to a large extent, that it did not explain why it was that it selected a lesion. Was it because of microcalcifications? Was it because of the shape or morphology. How certain was it? Was it 99% sure, 90% sure? And so if I had a resident or fellow that just told me, what they thought and couldn't explain why, I would be suspicious. And so I think one thing that's important is to have a system essentially explain why it is choosing something, and then allow you potentially to change the sensitivity and specificity. The other thing that scares me a little bit from a black box perspective is we've had reports in the news of cars that do autopilot, Teslas, are just randomly or non-randomly actually driving off the road and hitting emergency vehicles that have emergency lights. There's nobody at Tesla that knows or can explain why it is that it does that. All they know is that it's taken millions or billions of miles and it learns from that experience of driving. But the algorithm that's created, it's not clear why it is that it makes that particular error. And the challenge for me is when AI doesn't work, being able to trace back where is it in the algorithm that I need to change or fix. And I think this is one of the challenges that's different from CAD, where we could go back into the logic of the traditionally produced algorithms. So that's a concern. As Bram says, in many cases, it probably doesn't matter for certain types of applications, but for others, I think that explainability is going to go a long way toward adoption by radiologists trusting the AI algorithms.
Yeah, and I think you have to add that initially the first generation of mammography CAD was simply not good enough, right? So if an algorithm performs well, then I think there automatically people will trust it more. And I think that might be more important than explainability in some case. If it makes a mistake, we need procedures to follow up on how to improve the AI. That's why this FDA procedure that you mentioned, Elliot, is so interesting. In the Netherlands, we have, when there is a deadly incident on the road, there is always a formal investigation and a report is written. And I think we need something similar for these type of applications in healthcare, that as a radiologist, if you see that your AI system makes a big mistake, you need to be able to report that case, and somehow the industry needs to be able to improve their products and learning from these mistakes. And it will be difficult to set this up, but I think it is essential in the long term.
Yeah, Bram, we did an interesting project at University of Maryland where we took the results of AI and we found that it tended to overestimate certain things in older women and underestimate things in other populations. And what we found is that we were able to create a machine learning algorithm that would tailor it to our own population, take the results out of the box, and then essentially create a lens that would be a corrective lens for your own facility. And so I think the promise to be able to understand why it fails, when it fails, and then to record that, and then to correct that algorithm the same way we would correct a trainee in radiology is really exciting.
Yeah, I think we really need to help industry and define procedures how to do this, because right now these are still point solutions, right, that have been trained once and then they are released upon the world. And yeah, I think we need to have some procedures in place to change that.
I'm going to make this very quick, just to follow up to that, and then we'll get to some of the other questions. But I think you brought up maybe tangentially this idea of bias, though, in AI. And I think as we talk about algorithms that are trained for one specific purpose, they're often also trained on one specific cohort. And so much of the scientific literature, as we've heard over and over again, is focused very heavily on white men. And so how do we, it's just a plea to everyone on this call and to you guys in particular, how do we get the data? How do we aggregate that data, share it together so that we can train these algorithms on a wider, much more diverse cohort of population? If you have a quick answer to that, great. If not,
I think one quick answer is Bram was talking about tuberculosis algorithms. And one of the things, as you probably know, is TB manifests itself dramatically differently in different areas of the country because there are different variants of it. And so if you train on TB in Asia, it may be very different than in North America or Europe, et cetera, because they're truly different variants. And so I think that's one of many different examples of why it's so important that when one has an algorithm that one shares what is the population that the algorithm was initially trained on? And is there the capability of using the same approach to add additional types of populations and to understand that and to apply it? And what we've seen time and time again is what gets developed on one population doesn't seem to be anywhere near as high performing on another population.
Yeah, so that should be part of the procedures. We actually recommend everybody using our software to do a first test with your population, because indeed, if you have a high HIV in your population, it's completely different, the performance. This also holds for humans reading the X-rays, by the way, but you need to continuously do some quality control of all your reading processes, whether it's by computers or by humans.
Wonderful. That's great. I appreciate it. I'm going to try to get to some more of the questions from the chat. There's at least one here that talks about, do we believe that AI is going to bring an end to the basic radiology read?
Yeah, so I mean, there we are back with Professor Hinton and Andrew Ng, et cetera. I don't believe it will at all. I wonder if that question means, are we going to eliminate conventional radiographic interpretation, because some people may interpret the question that way. And I think, even conventional radiographs can be really challenging to interpret. So I think that humans and computers will be working together for a long, long time. I think for very specific applications, like finding lung nodules, intracranial hemorrhage, and other very narrow applications, I think that AI is going to be able to do a pre-read and become really, really very accurate. But I don't see humans being taken out of the equation. I realize in some areas outside of the US that conventional X-rays aren't even interpreted. They're just performed, and there's no radiologist that interprets them. And I could certainly see, as was the case with TB in Bangladesh, that one could have a preliminary interpretation done by AI, particularly when it had a high level of confidence. But I do not believe that anytime within the next short number of decades that we're going to replace radiology humans.
I think it's what you mentioned also about ultimately the interpretation part, right? We now have one software for chest X-ray, which detects, I think, 130 different signs, and the company advertises with that. So then you basically get a list of lots of things that you see and do not see in a particular exam, but that is not yet a conclusion, right? So radiologists still in the more difficult cases, there's a whole thought process where they also look at clinical information and actually try to find out what is going on with the patient and what is the logical next step, and do I need to get more information from my colleagues before I can say something? And that kind of conversation, it would be fantastic if we ultimately get thinking machines that can do this kind of reasoning, but we're not there yet.
The early residents, first and second years, get pretty good at making findings, but the later year residents and fellows start getting really good at having insights and understanding, and what is it that this means to the patient in the greater context. And I think that that's where humans really will be able to contribute. And I'm hoping AI in the future will get more sophisticated to be able to do that as well.
Yeah, and perhaps and I think, Bram, you mentioned this in your talk, when we look at reducing the normal exam, or reducing the burden of the normal exam, you talk about mammography, and perhaps that was where the question was, is that a reality across a broad swath of sort of diagnostic cases where we might be able to take and just get rid of or deprioritize the normal reads, and then really focus the radiologist's time on the more difficult tasks or the more interesting ones with actual findings?
Yeah, I think we should do that. We cannot afford CT lung cancer screening if you do the calculations, if you let radiologists read all these cases. It's just not possible. But you should delegate that few percent of the cases to a board of experts to review it. But the bulk should be done automatically in screening applications. This is different from clinical radiology.
Absolutely. There's a question here about cybersecurity. So, certainly as the data starts to flow around the world into these algorithms, into the cloud, there's a larger risk of this data becoming leaked or used for nefarious purposes. What's both of your takes on sort of both where we are and where we need to get as far as the securing our data and the diagnoses and patient health information.
Yeah. So I mean, from my own perspective, I think it's a really valid point that as we interchange information digitally, which is much more convenient and much smarter, I think we need to take into account a variety of different evolving technologies that will allow us to be able to better encrypt the data. The potential to be able to store data encrypted instead of just encrypting it when you move it from one location to the other. The ability to be able to potentially look at blockchain technologies to minimize the likelihood that images get changed as time goes on. And I know there are some efforts within the DICOM community to acknowledge that the DICOM developed in the 1980s was not meant to in any way be secure. It was just meant to work. And so as we rethink DICOM, having something that's interoperable with DICOM, but yet allows us to be able to, within the standard, store data in an encrypted format so that it could not be stolen or could not be altered, I think is the direction that we're going. I think you're going to see in the next 5 years some significant developments in allowing better encrypted storage. It has not been a priority for the medical imaging community until just recent years. And from what I'm aware of, there are a number of really interesting efforts to make that far more secure without sacrificing performance.
Great. Let's move to another question. And this maybe is for Bram, but I'd like to hear both of you. How will AI impact third world countries or other areas in the US, for example, where it's more rural, where there's less access? Is this a boon? Is this, I've also heard people worry that with the rise of AI, we're going to increase the disparity in health, increase that gap. And are there ways that we can use AI to either decrease or completely do away with that, that sort of social determinants of health and other things like that? Please comment.
Well, I think it's a great opportunity. What you see in countries where the healthcare system is not as advanced as in some Western countries, or economy in general, that they skip certain steps, right? So in Africa, they never built a landline phone infrastructure. They directly went to mobile phones. I think also they will not develop all these medical specialties. So also pathologists, radiologists, they basically are hardly any of such medical specialists in Africa. What you do see is that you get general doctors, clinical officers, and I think they will embrace AI tools, and hopefully they can refer cases, because it's all digital information, to specialists. They don't even have to be in the country. But I think it is an illusion that they will build up the same type of medical specialties as we have it. And they will use AI from the start. And I think that this is an opportunity to just make healthcare more efficient. Right now in my country, we are on a disaster course. We've seen this with COVID. It's personnel shortages which is causing all the problem. In this case, ICU personnel. So we need to have AI solutions to work with humans in the most efficiently possible way. And if we need human experts, we need to delegate the right cases that really need review by human experts to human experts. But we need everything, I think, to solve the healthcare crisis that is approaching us.
And I believe that I agree that AI will democratize expertise throughout the world, and that we will see a significant decrease in the disparity with regard to expertise. I mean, Bram talked about some of the TB applications and WHO, and already, as he's described, what we have for them now is a significant improvement over what they had with the human readers that had lower amounts of expertise. One thing I'm concerned about is if the WHO, as Bram indicated, is essentially, embracing AI in those populations, I'd like to see some level of testing so that WHO would have some mechanism of being able to, separate the better performing algorithms from the ones that perform less well. It's an issue that I think is going to happen as we start seeing apps in app stores start claiming to be able to interpret chest radiographs for TB or read MRIs of the knee, et cetera. I think there needs to be some mechanism to separate really strong performers based on really strong, large databases from those that are cropping up that really have not taken the same amount of care and don't have the same level of performance.
Yeah, absolutely. I think these initiatives are now coming. Various organizations are trying to set this up, and that's very good. And now it's needed. Actually, 20 years ago, the software was not that good. So you could spend a lot of time on validation and you would find out that it's not that good. But now we have so much software on the market, and some of it I think is really good, and some of it is not good enough. That's clearly what we get back from our radiologists. So testing is going to be absolutely crucial.
And the gold standard can be really a challenge to set. We have 2 to 3 million tuberculosis cases that we have in a database that we're looking at. And one of the things that we find is that we have radiologists who have incredible levels of expertise. One of them is very sensitive, doesn't want to miss a case of tuberculosis. Another is very specific, doesn't want to overcall it. They're seeing the same things, they have the same level of expertise, but does my algorithm create a Dr. White interpretation or a Dr. Galvin interpretation? The residents who know which radiologist is going to read the study, knowing each one of them are equal, incredible experts, they will read it according to who is the radiologist that is going to be interpreting it. And so I think we need to figure out what is our gold standard and what is it that we're going for. And that's going to be tricky moving forward, as we're finding. We have AI algorithm that can read like Dr. White, another one that reads like Dr. Galvin, one that reads halfway in between. Which one do you want? And so I think those sorts of subtle questions will become more important as we become more advanced and sophisticated in our applications.
Yeah. Yes, indeed. What do we want, right? I think that's usually the most important question when you have new technology. How do you want to use it?
Yeah, and we have a lot of patients where we know whether they actually subsequently were tested positive for TB, but that doesn't mean there was any manifestation of TB on their chest radiograph. So is truth, whether they actually clinically ever had it or were tested positive serologically, or is truth the world expert? And how does one determine that? And so I think that whole idea of what is ground truth, as these AI algorithms are starting to approach or exceed human level performance, is really going to be fascinating.
Yeah, I mean, I think you're hitting on some of the reasons why Hinton was just wrong. And it's not, I think he was absolutely right that there will be algorithms that outperform, but it's going to be so narrow that the subtleties and all those complexities that go in, it's going to be almost impossible to build into any one algorithm. So it's going to be this marriage of the experts like yourselves and great algorithms that can give you more data and more insight into those into the situation that you're in. I think I'm going to end it here. We're a little bit over time. It's been a fantastic converation. So I just want to say thank you to all who joined, and a special thank you both Elliot and Bram. Fantastic talks, wonderful conversation. And I look forward to seeing you both soon.
Thanks so much. It's really exciting to see Canon in the AI game. And so I'm really looking forward to see how things progress. So thanks so much.
Wonderful.
Thank you.
Thanks all.